During the lecture, we discussed that we can easily sample random numbers from a mixture of normal distributions using a two-step algorithm. I want to illustrate that algorithm now using the R software. In this particular example, I'm going to generate 50 observations from a mixture of two normals. The weights of the two components are 0.6 and 0.4. The means of the two normals involved in the mixture are 0 for the first one and 5 for the second one. And the standard deviations are 1 and 2 for each one of the components. Now, if you remember the algorithm we discussed in the lecture, that it has two steps. The first step, in the first step, we just decide which component generates each one of the observations. And we can easily do that in R using the sample command. So we're going to sample n numbers, in this case 50. Each one of those numbers can take only two values, 1 or 2, 1 to 2. We're going to be doing sampling with replacement. And the probability of selecting each one of the two numbers is given by the vector W of weights that we defined before. Now that we have defined what component generates each one of the observations, we can just use that information to use the R norm command to generate, again, 50 values. And this vector mu of CC and the vector sigma of CC just contains the mean and the standard deviation associated with each one of those observations. So let's run this code and explore a little bit what was done. The vector CC, if you look at it, contains numbers between 1 and 2, because I only have two components. And the vector mu contains just two numbers, 0 and 5, that correspond to the means of the two components. If you look at what mu of CC is, this is just another vector of the same length as CC, in this case 50. And the entries of that vectors are 5, where CC was 2, and 0, where CC is 1. And that's because by evaluating this CC vector into mu, we are just selecting the entries of mu that correspond to the components that we looked at. So if you think in terms of the R norm function, what this is doing is saying the first random variate that is going to be generated by our norm is going to have mean 0. The second is going to have the first one is going to have mean 5. The second one means 0. The third one means 0. The fourth one means 5, and so on. And something similar happens if you do sigma of CC. So now our vector X contains those random numbers. And you can see that observations that come from component 2 that has a larger mean tend to be large, in the order of 6 or 5. So both of these numbers are generated from the second component. And you can see that here. And numbers that are generated from this first component, just like this and this, that correspond to the first component, tend to be lower, in some cases negative, in some cases positive, but closer to 0 than to 5, as we would expect. Now, we can represent this graphically by essentially repeating the plot that we had constructed before for this mixture, and adding the points that were generated to it. And that's what this graph shows. So you can see this is the density of the mixture of normals. We had already seen it before. And what I have done now is to add the points that have been sampled down here in the graph. We could even slightly improve this by adding color to those points according to the component that generated them. And that's very easy to do. And now you can see that the majority of the points that are under this first little mountain the majority are black. And the majority of the points that are under the second little mountain are red. But there is some confusion here in the middle where the two intercept, and there are some observations that could belong to one place or the other. So that is going to be a very common phenomenon in mixture models, and it's one that we will be exploring in more detail later.